Okay, hi everyone, welcome back to this video series on cryptocurrency, making trustless channels. The channel we just described works, but only if both parties cooperate without any failures or attempts to cheat. Let's look at some of the scenarios that break this channel and see what is needed to fix those. Once a funding transaction happens, Emma needs Fabian's signature to get any money back. If Fabian disappears, Emma's funds are locked in at 2 of 2 and effectively lost. This channel as constructed leads to a loss of funds, and if one of the parties disconnects before there is at least one commitment transaction signed off by both parties. While the channel is running, Emma can take any of the commitment transactions Fabian has countersigned and transmit one to the blockchain. Why pay for 600 seconds of video if she can transmit commitment transaction #1 and only pay for 1 second of video? The channel fails because Emma can cheat by broadcasting a prior commitment that is in her favor. Both of these problems can be solved with time locks. Let's see at how we could use transaction level time locks, lock time. Emma cannot risk funding a 2 of 2 multisig unless she has a guaranteed refund. To solve this problem, Emma constructs the funding and refund transaction at the same time. She signs the funding transaction but doesn't transmit it to anyone. Emma transmits only the refund transaction to Fabian and obtains his signature. The refund transaction acts as the first commitment transaction, and its time lock establishes the upper bound for the channel's life. In this case, Emma could set the end lock time for 30 days or 4,320 blocks into the future. All subsequent commitment transactions must have a shorter time lock so that they can be redeemed before the refund transaction. Now that Emma has a fully signed refund transaction, she can confidently transmit the signed funding transaction, knowing that she can eventually, after the time lock expires, redeem the refund transaction even if Fabian disappears. Every commitment transaction the parties exchange during the life of the channel will be time locked into the future, but the delay will be slightly shorter for each commitment. So the most recent commitment can be redeemed before the prior commitment it invalidates. Because of the end lock time, neither party can successfully propagate any of the commitment transactions until their time lock expires. If all goes well, they will cooperate and close the channel gracefully with a settlement transaction, making it unnecessary to transmit an intermediate commitment transaction. If not, the most recent commitment transaction can be propagated to settle the account and invalidate all prior commitment transactions. For example, if commitment transaction 1 is time locked to 4,320 blocks in the future, then commitment transaction #2 is time locked to 4,319 blocks in the future. Commitment transaction #600 can be spent 600 blocks before commitment transaction #1 becomes valid. Figure 12.7 shows each commitment transaction setting a shorter time lock, allowing it to be spent before the previous commitment becomes invalid. Each subsequent commitment transaction must have a shorter time lock so that it may be broadcast before its predecessors and before the refund transaction. The ability to broadcast a commitment earlier ensures it will be able to spend the funding output and preclude any other commitment transaction from being redeemed by spending the output. The guarantees offered by the Bitcoin blockchain, preventing double spends and enforcing time locks effectively allows each commitment transaction to invalidate its predecessor. State channels use time locks to enforce smart contracts across a time dimension. In this example, we saw how the time dimension guarantees that the most recent commitment transaction becomes valid before any earlier commitments. Thus, the most recent commitment transaction can be transmitted, spending the inputs and invalidating prior commitment transactions. The enforcement of smart contracts with absolute time locks protects against cheating by one of the parties. This implementation needs nothing more than absolute transaction level time locks, end lock time. Next, we'll see how script level time locks, check time lock verify and check sequence verify can be used to construct more flexible, useful and sophisticated state channels. The first form of unidirectional payment channel was demonstrated as a prototype video streaming application in 2015 by an Argentinian team of developers. You can still see it at streamium.io. Time locks are not the only way to invalidate prior commitment transactions. In the next sections, we will see how a revocation key can be used to achieve the same result. Time locks are effective, but they have two distinct disadvantages. By establishing a maximum time lock when the channel is first opened, they limit the lifetime of the channel. Worse, they force channel implementations to strike a balance between allowing long-lived channels and forcing one of the participants to wait a very long time for a refund in the case of premature closure. For example, if you allow the channel to remain open for 30 days by setting the refund time lock to 30 days, if one of the parties disappears immediately, the other channel must wait 30 days for a refund. The more distant the endpoint, the more distant the refund. The second problem is that since each subsequent commitment transaction must decrement the time lock, there is an explicit limit on the number of commitment transactions that can be exchanged between the parties. For example, 30-day channel setting the time lock of 4,320 blocks into the future can only accommodate 4,320 intermediate commitment transactions before it must be closed. There is a danger in setting the time lock commitment transaction interval at 1 block. By setting the time lock interval between commitment transactions to 1 block, a developer is creating a very high burden for the channel participants, who might have to be vigilant, remain online and watching, and be ready to transmit the right commitment transaction at any time. Now that we understand how time locks can be used to invalidate prior commitments, we can see the difference between the closing channel cooperatively and closing it unilaterally by broadcasting a commitment transaction. All commitment transactions are time locked. Therefore, broadcasting a commitment transaction will always invoke waiting until the time lock has expired. But if the two parties agree on what the final balance is and know they both hold commitment transactions that will eventually make the balance a reality, they can construct a settlement transaction without a time lock representing the same balance. In a cooperative close, either party takes the most recent commitment transaction and builds a settlement transaction that is identical in every way except that it omits the time lock. Both parties can sign this settlement transaction knowing there is no way to cheat and get a more favorable balance. By cooperatively signing and transmitting the settlement transaction, they can close the channel and redeem their balance immediately. Worst case, one of the parties can be petty, refuse to cooperate, and force the other party to do a unilateral close with the most recent commitment transaction. But if they do that, they have to wait for their funds too. Asymmetric revocable commitments. A better way to handle a prior commitment states is to explicitly revoke them. However, this is not easy to achieve. A key characteristic of Bitcoin is that once a transaction is valid, it remains valid and does not expire. The only way to cancel a transaction is by double spending its inputs with another transaction before it is mined. That's why we use time locks in the simple payment channel example above to ensure that more recent commitments could be spent before the older commitments were invalid. However, sequencing commitments in time creates a number of constraints that make payment channels difficult to use. Even though a transaction cannot be cancelled, it can be constructed in such a way to make it undesirable to use. The way we do this is by giving each party a revocation key that can be used to punish the other party if they try to cheat. This mechanism by revoking prior commitment transactions was first proposed as part of the Lightning Network. To explain revocation keys, we will construct a more complex payment channel between two exchanges run by Hitesh and Irene. Hitesh and Irene run Bitcoin exchanges in India and the USA respectively. Customers of Hitesh's Indian exchange often send payments to customers of Irene's USA exchange and vice versa. Currently, these transactions occur on the Bitcoin blockchain, but this means paying fees and waiting several blocks for confirmations. Setting up a payment channel between the exchanges will significantly reduce the cost and accelerate the transaction flow. Hitesh and Irene start the channel by cooperatively constructing a funding transaction, each funding the channel with a 5 Bitcoin. The initial balance is 5 Bitcoin for Hitesh and 5 Bitcoin for Irene. The funding transaction locks the channel state in a 2 of 2 multisig, just like the example of a simple channel. The funding transaction may have one or more inputs from Hitesh adding up to 5 Bitcoin or more, and one or more inputs from Irene adding up to 5 Bitcoin or more. The inputs have to slightly exceed the channel capacity in order to cover the transaction fees. The transaction has one output that locks the 10 total Bitcoin to a 2 of 2 multisig address controlled both by Hitesh and Irene. The funding transaction may also have one or more inputs returning change to Hitesh and Irene if their inputs exceed their intended channel contribution. This is a single transaction with inputs offered and signed by two parties. It has to be constructed in collaboration and signed by each party before it is transmitted. Now, instead of creating a single commitment transaction that both parties sign, Hitesh and Irene create two different commitment transactions that are asymmetric. Hitesh has a commitment transaction with two outputs. The first output pays Irene the 5 Bitcoin she is owed immediately. The second output pays Hitesh the 5 Bitcoin he is owed, but only after a time lock of 1000 blocks. The transaction output looks like this: input 2 of 2 funding, output signed by Irene, output 0, 5 Bitcoin, Irene, public key, check sig, output 1, 1000 blocks, check sequence verify drop, Hitesh's public key, check sig. Irene has a different commitment transaction with two inputs. Irene has a different commitment transaction with two outputs. The first output pays Hitesh the 5 Bitcoin he is owed immediately. The second output pays Irene the 5 Bitcoin she is owed, but only after a time lock of 1000 blocks. The commitment transaction Irene holds signed by Hitesh looks like this: Irene 2 of 2 funding, output signed by Hitesh, output 5 Bitcoin, Hitesh's public key, check sig, output 1, 1000 blocks, check sequence verify drop, Irene's public key, check sig. This way each party has a commitment transaction spending the 2 of 2 funding output. This input is signed by the other party. At any time, the party holding the transaction can also sign completing the 2 of 2 and broadcast. However, if they broadcast the commitment transaction, it pays the other party immediately, whereas they have to wait for a short time lock to expire. By imposing a delay on the redemption of one of the outputs, we put each party at a slight disadvantage when they choose to unilaterally broadcast a commitment transaction, but a time delay alone isn't enough to encourage fair conduct. Figure 12.8 shows 2 asymmetric commitment transactions where the output paying the holder of the commitment is delayed. Now we introduce the final element of the scheme, a revocation key that allows a wronged party to punish a cheater by taking the entire balance of the channel. Each of the commitment transactions has a delayed output. The redemption script for that output allows one party to redeem it after 1000 blocks, or the other party to redeem it if they have a revocation key. So when Hitesh creates a commitment transaction for Irene to sign, he makes the second output payable to himself after 1000 blocks, or to whoever can present a revocation key. Hitesh constructs this transaction and creates a revocation key that he keeps secret. He will only reveal it to Irene when he is ready to move to a new channel state and wants to revocate his commitment. The second output looks like this. Output 05 Bitcoin Irene public key check sig. Output 15 Bitcoin if revocation penalty. Output revocation public key else 1000 blocks check sequence verified drop Hitesh's public key end if check sig. Irene can confidently sign this transaction. Since it is transmitted, it will immediately pay her what she is owed. Hitesh holds the transaction but knows that if he transmits it at a unilateral channel closing, he will have to wait 1000 blocks to get paid. When the channel is advanced to the next state, Hitesh has to revoke this commitment transaction before Irene agrees to sign the next commitment transaction. To do that, all he has to do is send the revocation key to Irene. Once Irene has a revocation key for this commitment, she can sign the next commitment with confidence. She knows that if Hitesh tries to cheat by publishing the prior commitment, she has a revocation key to redeem Hitesh's delayed output. If Hitesh cheats, Irene gets both outputs. The revocation protocol is bilateral, meaning that in each round, as the channel state is advanced, the two parties exchange new commitments, exchange revocation keys for the previous commitment, and sign each other's commitment transactions. As they accept a new state, they make the prior state impossible to use, giving each other the necessary revocation keys to punish any cheating. Let's look at an example of how it works. One of Irene's customers wants to send 2 Bitcoin to one of Hitesh's customers. To transmit 2 Bitcoin across the channel, Hitesh and Irene must advance the channel state to reflect the new balance. They will commit to a new state, state number 2, where the channel's 10 Bitcoin are split, 7 Bitcoin to Hitesh and 3 Bitcoin to Irene. To advance the state of the channel, they will each create new commitment transactions reflecting the new channel balance. As before, these commitment transactions are asymmetric, so that the commitment transaction each party holds forces them to wait if they redeem it. Crucially, before signing a new commitment transactions, they must first exchange revocation keys to invalidate the prior commitment. In this prior case, Hitesh's interests are aligned with the real state of the channel and therefore has no reason to broadcast the prior state. However, for Irene, state number 1 leaves her with a higher balance than state 2. When Irene gives Hitesh the revocation key for her prior commitment transaction state number 1, she's effectively revoking her ability to profit from regressing the channel to a prior state, because with the revocation key, Hitesh can redeem both outputs of the prior commitment transaction without delay, meaning if Irene broadcasts the prior state, Hitesh can exercise his right to take all of the outputs. Importantly, the revocation doesn't happen automatically. While Hitesh has the ability to punish Irene for cheating, he has to watch the blockchain digitally for signs of cheating. If he sees a prior commitment transaction broadcast, he has 1,000 blocks to take action and use the revocation key to thwart Irene's cheating and punish her by taking the entire balance, all 10 Bitcoin. Asymmetric revocable commitments with relative time locks, CSV, are a much better way to implement payment channels and verify significant innovation in this technology. With this construct, this channel can remain open indefinitely and can have billions of intermediate commitment transactions. In prototype implementations of Lightning Network, the commitment state is identified by a 48-bit index, allowing more than 281 trillion 2.8 by 1014 state transactions in any signed channel. So I'm going to leave it here today for this video. If you'd like listening, please consider like, sharing and subscribing. Thank you.